In the same way that capacitors store potential energy in a circuit, we see now that the inductor, the ideal case being the solenoid that we've been studying in class, the inductor also stores energy within its volume. You will see the expression for energy density in a magnetic field, analogous to the expression that you saw for the energy density in electric fields. Energy density, lowercase u, is the magnetic field squared divided by 2 mu naught. In the volume of the inductor is where we find the magnetic field. The ideal case, the magnetic field outside the solenoid was 0. So we'll take the total potential energy stored inside the solenoid to be the density times the total cylindrical volume that it encloses. Using Ampere's law, earlier we discovered the magnetic field inside the solenoid was mu naught Ni, where N is your turns density, or number of turns of wire divided by the length of the solenoid. So if we pack all of these expressions together, our energy density sitting here is magnetic field squared. So you have mu naught Ni squared over 2 mu naught times the volume of the cylinder, which is just its cross-sectional area times its length. Well, this potential energy, you can see, has current squared as a 1/2, and then a bunch of constants that depend only on the physical characteristics of the device. So we could simplify this expression for potential energy by defining something called the self-inductance of that solenoid. It is the cross-sectional area times the length, together they make the volume, times mu naught times the turn density squared, if you're just dealing with the standard cylindrical solenoid case. And you'll recall there was a similar expression for the parallel plate capacitor that only depended on its physical characteristics. Permittivity, what was inside of it, the area of each plate divided by the separation of the plates. Just like the permittivity could be modified by adding a dielectric material, we would say permittivity of the dielectric was the dielectric constant kappa times epsilon naught. We have a similar expression that will define the permeability of a material as an analogous kappa sub m for magnetism times mu naught. So we'll look at some examples of how that will improve the behavior of the inductor in class. But for now, taking this definition of self-inductance, we have a simple expression here, which is that the total potential energy in the device is 1/2 times the self-inductance L times the current squared. And though we derived this using the standard cylindrical solenoid, it will be valid for any inductor having self-inductance L. The unit of self-inductance, the SI unit, is called the Henry. It's equivalent, you can see here, to energy divided by current squared. So the joule per amp squared is the Henry. It is also equivalent to an ohm times a second. We will apply this in an application called the LC circuit, where we will see energy being stored at some time in the inductor, the L of the circuit, and shuffling back and forth that energy will pass it to a capacitor, the C, in the LC circuit.